হ্যালো।
হ্যালো, 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 হ্যালো।
ইয়েস ম্যাম।
হ্যাঁ, গৌরব?
না ম্যাম,
হ্যাঁ,
আমি গৌরব নই।
গার্গী? হ্যালো? হ্যাঁ, গার্গী? হ্যাঁ, গার্গী? না, আমি শুনতে পাচ্ছি না তোমাকে। তুমি আমার শুনতে পাচ্ছ তো? আমি গার্গী বলছি না? আচ্ছা, হ্যাঁ, গার্গী, তুমি একটা জিনিস তোমাকে বলবো বলে, যে যখন আমরা কেউ বলবো, ধরো শ্রীমন্তী দি, আমি, আলু যখন বলবো, আমাদেরটা ছোট্ট এতে রাখবে, ওই বড় যে স্ক্রিন সেভারটা আছে না, ওটাকেই মেন রাখবে, আর আমাদের ছোট্ট করে দেখাবে। আমাদের ফুল স্ক্রিন দেওয়ার দরকার নেই। হ্যাঁ, স্পিকার ছাড়া কাউকে ফুল স্ক্রিন দেওয়ার দরকার নেই, ওই ছোট করে একদিকে থাকবে। আর হ্যাঁ, হ্যাঁ, পোস্টারটা তাও যদি ও অন অফ হয়ে যায়, তবুও তোমার কাছে ব্যাকআপটা ওকে বলেছি দিয়ে দিতে, বা তনিমাকেও একটা ব্যাকআপ। হ্যাঁ, হ্যাঁ, হ্যাঁ। কারণ হচ্ছে না, এখন ওই বৃষ্টির জন্য ইন্টারনেট কানেকশনের। হ্যাঁ, হ্যাঁ, ওইটাই তো খুব অসুবিধে, বুঝতে পারছিলাম না। হ্যাঁ, আর ডক্টর ডির আমাকে লিখেছেন, উনি বিএসটি টা ধরেছেন, মানে বাংলাদেশে। আবার আমি তোমাকে গ্রুপে লিখলাম। না, উনি তারপরে, আমি ওই জন্য পাঠালাম ওনার স্ক্রিনশটটা আবার 50 মিনিট বাদে, মানে ধরো আর ওই 4টে বাজতে 10-15 মিনিট আগে উনি ঢুকবেন, ওনাকে এ করে দিয়ে। হ্যাঁ, আর হ্যাঁ, আর আমরা যখন কেউ কিছু বলবো, আমাদের ছোট করে যে এ দিয়ে দিও, আমাদের ওই বড় স্ক্রিনটা যেটা আমাদের মেন, যে ওই এটা, ওটাকে মেন হাইলাইট করে আমাদের ছোট ছোট করে দেখিয়ে দিও। ঠিক আছে, আর যে যার বলার পরে ওটা আমরা স্ক্রিনটাকে আমরা এমনিতেই ভিডিওটা অফ করে দেবো। হ্যাঁ, ঠিক আছে, ওকে। হ্যাঁ,
Yes.
গার্গী আমায় শোনা যাচ্ছে আলো দি?
হ্যাঁ শোনা যাচ্ছে শোনা যাচ্ছে।
আচ্ছা
Hello. Hello. Hello.
ঠিক আছে, কিছু করতে হবে না, এবার অটোমেটিক মিটিং শুরু হবে।
ঠিক আমি ধরে থাকি এরকম। এরকম করে থাকে নাকি চড়া দিতে হবে?
Test.
हेलो गार्गी, हेलो गार्गी, हेलो গার্গী শুনতে পাচ্ছো? হ্যালো,
হ্যাঁ মধুমিতা দি শোনা যাচ্ছে শোনা যাচ্ছে।
তুমি একটু বলে দাও না পার্টিসিপেন্টসদের অডিওটা অফ করতে, খুব নয়েজি হচ্ছে। দেখো অডিও ভিডিও অনেকেই অন করে আছে। আমি লিখলাম। হ্যালো তনিমা বললি না গার্গী?
শোনা যাচ্ছে।
আচ্ছা
Hello. Hello. You.
গাড়ি, হ্যালো হ্যালো, আরে সব ভিডিও করে।
হ্যাঁ হ্যালো হ্যালো মধুমিতা দি, হ্যালো।
হ্যাঁ হ্যাঁ গার্গী বলো।
হ্যাঁ বলছি তোমার তো স্ক্রিনটা শেয়ার করে রাখো, হ্যাঁ পোস্টারটা।
আমি না তো।
তাহলে কে করছে?
হ্যাঁ পোস্টার শেয়ারিং শর্মি করছে।
ও আচ্ছা, তাহলে ওকে একটু বলো না মানে ওর স্ক্রিনটা ইয়ে করে শেয়ার করে রাখতে। হ্যাঁ
আচ্ছা আচ্ছা, আমি ওকে কি করে বলি বলো তো, চ্যাট বক্সে লিখবো নাকি?
ফোন 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 ফোন
ফোন করে দিচ্ছি, ঠিক আছে।
আমি কি এখন আমি আছি অনলাইন, আমি কি শেয়ার করে দেবো
আচ্ছা,
স্ক্রিনটা?
হ্যাঁ স্ক্রিনটা শেয়ার করে
হ্যাঁ,
দাও, হ্যাঁ
করে দে,
স্ক্রিনটা
করে দে।
শেয়ার করে দাও।
এটা শেয়ার করা থাকলে প্রবলেম হবে না? গার্গী দি, হ্যালো গার্গী দি, আছো?
শর্মি আমি আছি, কিছু কি
হ্যাঁ
বল।
মধুমিতা দি, আমি যদি স্ক্রিন শেয়ার করি না, আমি তাহলে মানে ভিডিও দেখতে পাচ্ছি না আর কি।
মানে ও মনে হয় বললো ওই যেটা স্ক্রিন খালি থাকার সময় থাকবে ওইটুকু শেয়ার করে দে নাকি, আমি বুঝতে পারছি না।
না মানে আমি শেয়ার করে
এইটা,
রাখতে পারি,
এই
বাট
লেখাটা থাক, এই
হ্যাঁ
লেখাটা
এই
থাক।
লেখাটাই থাক।
ওকে ওকে,
ব্যাস,
তাহলে
হ্যাঁ
আমি আচ্ছা ঠিক আছে সাইডে দেখতে পাচ্ছি। ওকে, থ্যাংক ইউ।
ওকে ওকে, হ্যাঁ।
হ্যালো, হ্যাঁ শর্মি, হ্যালো।
শর্মি,
হ্যাঁ বলছি না, শোনো মধুমিতা দি, তুমি শুনে রাখো, ওকে একটু বলে দিও যে মানে ওর পোস্টারটা যেন শেয়ার করা থাকে একমাত্র স্পিকার বললেই যেন ওটাকে সরিয়ে দেয়, বাকিরা থাকে বললে অসুবিধা, ওরকমই
মানে
রেখে দেয়।
স্টপ শেয়ারিং করে দেবো তো? স্পিকার
ঠিক
বলতে
আছে।
হ্যাঁ হ্যাঁ, শুধু স্পিকার বললেই স্টপ শেয়ারিং করে দেবে, ঠিক আছে?
ওকে ওকে ওকে।
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 মধুমিতা দি, আইডি এখনো ঢোকেনি?
ছিলেন তো।
দেখতে পাচ্ছি না কিন্তু, স্পিকার তো এসে গেছে।
হ্যাঁ সেটাই তো। ম্যাডাম তো ছিলেন।
দেখতে পাচ্ছি না।
আচ্ছা গার্গী, আমি কি ভিডিও অফ করে দেবো?
হ্যাঁ মানে শুধু মানে এই স্ক্রিন শেয়ার করা আছে তো, ঠিক আছে, এবার অফ করে দিতে পারো।
ওকে।
How many participants do we have? 69 already. Oh gosh.
Hello, Indrila.
Can you hear me?
Yes.
Yes,
Sure.
yes, I can hear you. ID, Dr. Reed is on air. Welcome him, please. Dr.
Oh
Reed
yes,
is on
good
air.
afternoon. Hello.
Hello, Doctor.
Good afternoon, Dr. Reed. I mean,
Good
good
morning. Very
morning
good
in
morning.
your home country.
Well,
Yes.
yes, morning here still, just about.
Yeah. Yeah.
Okay, do you know how many participants you are expecting today?
Indrani,
Yes.
Indrani, Professor Reed is asking something about the number of participants you're
Oh,
expecting.
Gargi can, yeah, Gargi can say. Gargi. Hello, Gargi. Can you hear me?
Yeah. I don't actually. Oindrida can say.
I think around about 150 to 200. I mean, total number of registered candidates is about 550, around about 550. So we can
my
expect at least 200 to 250 people.
Oh
People
my
are just
goodness.
joining in, yeah. Hopefully, yeah. It's very inclement weather. Yeah, so yeah, hopefully everyone will connect within the next 15 to 20 minutes.
Hmm. Shall I just try sharing my screen just to check that it works okay?
Yes. Yes.
Yeah.
Let me just try. Let me see, share screen. On the right page. So I can do. Yeah.
These sessions are chiefly aimed at the speaking audience to mitigate this type of monotony of the land and give them a sense of relief and revival. The pandemic is rocked them of their own regular well down, but it is also pushed towards a new understanding of nature. People nowadays are finding time to do.
Right, I hope that works okay. Can you see the screen okay?
Yes, sir. Yes, sir.
That's great. Okay.
Yeah.
All right, well, I'll stop sharing for the time being just to return to normal.
Hello, Indrani.
Yes.
Indrani,
Shrisha.
when do you propose to begin? Is Alo here? Has Alo arrived?
She can start.
Yes, I'm here.
Yes, she's here. Can we start, ID? Can we start?
Yes.
Shall we start?
I think, yeah, it's just 4 o'clock and I think we can start straight
Yes.
away.
Yes. Alo, please.
Okay, Indrani, do you want to
Am
say
I
any words in
audible,
introduction? Or,
Yeah, I'm here. Alo will start.
Alodi, you can
I think some network
Am I
problem is
audible?
there. Yes.
Yes,
Yeah.
Alodi, you can start.
Thank you. A very good afternoon to all of you. I'm Alo Guho of the Department of Geography of St. Anandram Jaipuria College, Kolkata. On behalf of the Departments of Botany and Geography and on behalf of our college, we extend our warm welcome and heartiest greetings to everyone present here today. We are grateful to our principal, Sir, Dr. Ashok Mukhopadhyay, for his encouragement and guidance regarding this webinar. Thank you, sir. We are honored to have Dr. Peter Reed, Professor of Physics, University of Oxford, UK, as our distinguished speaker today. We welcome you, sir. We welcome all dear colleagues and staff of our institution to our webinar. We are privileged to have you here and we thank all of you for your support. We extend our greetings to all the faculty members of various colleges and universities present here today. And we thank you for your response and interest in our webinar. We are also delighted to have our dear students here today and also students from various other colleges and universities, both within India and abroad. We are thankful to the internal quality assurance cell of our college, members of the organizing committee, technical assistance team, and everyone of our college involved in this endeavor for guiding and assisting us. This webinar series titled Connecting with Nature is an attempt to strengthen our bond with nature, to care for our Mother Earth, and in the long run, learn to care for each other, especially during these trying times. I now invite Dr. Srimanti Chaudhary of the Department of English of our college and request her to share her views on today's theme. Thank you all. Over to you, Srimanti ma'am.
Thank you, Alo. And everyone, on behalf of St. Anandram Jaipuria College, it is my pleasure to introduce the theme of today's webinar and the future editions of the webinar in the coming months. These sessions are chiefly aimed at the student audience to mitigate the stifling monotony of their life and give them a sense of release and revival. The pandemic has robbed them of their known regular world, no doubt, but it has also pushed them towards a new bonding with nature. People today are finding time to gaze passionately at the changing colors of the sky and observe minutely the trees and birds and tiny creatures around. Nature and environment have suddenly claimed the focus of our attention. Today's topic, climate and atmospheric circulation regime, putting the Earth in its planetary perspective, is part of the larger theme of the webinar series, namely connecting to nature. The theme is universal, essential, and subject to endless exploration and interrogation. In the Vedic times, nature or environment was conceived holistically, comprising the 5 elements: earth, water, fire, air, and sky.
and embracing both biotic and non-biotic, that is living and non-living components. A strong sense of eco-ethics pervaded ancient Indian culture. Mention was made in the Vedic texts of environmental protection and ecological balance. For any inadvertent action leading to the earth's injury, there were prayers for forgiveness, such as this from the Atharva Veda. Whatever I dig from thee, O earth, may that have quick recovery again. O purifier, may we not injure thy vast heart. The worshipful attitude of Indians towards an all-inclusive nature shows itself in the very concept of Mother Durga and her family. The idols are symbols of human virtue and vices, and the animals are representatives of almost every species of the animal world, from the wild lion to the herbivorous elephant, the reptile serpent, the aquatic swan, the nightbird owl, forester peacock, and the rodent rat. Ganesha's wife, Kolabo, is actually a bunch of 9 medicinal plants termed Oshadhi, and is worshipped at the very beginning of the elaborate puja process, indicating the ancients' awareness of life consciousness in plants. We in the post-industrial age have violated this reverence towards nature and disturbed its inclusivity and balance. Nature likewise has retaliated in the form of melting glaciers, cloudbursts and flash floods, air pollution, forest fire, holes in the ozone layer, and irregular climatic condition. Going back to the ancients again, we cannot help but recall their concept of cosmology, comprising the earth, the heavens, and the atmosphere or antariksh in between. Known as Paryavaran in Sanskrit, the atmosphere was supposed to be a protective covering or safety net around the planet Earth. Depletion in this covering, owing to irresponsible human act, has led to increased warming of the Earth's surface and the consequent climatic disaster. We look forward to the lecture by Professor, a physicist at the University of Oxford, to guide us towards a new understanding of the atmospheric dynamics of our planet Earth. In view of the practical necessities of modern civilization, we need to strike a judicious balance between man in nature and man versus nature, and restrict our activities to a sane and rational level. To end my thoughts, I would like to quote again a few lines of prayer from the Rig Veda. Do not harm the environment. Do not harm the water and the flora. Earth is my mother. I am her son. Tranquility be to the atmosphere, to the waters, to the crops, and the vegetation. Thank you. And now, to introduce our distinguished speaker, Professor Peter Reed, eminent scholar and teacher at the University of Oxford, I call upon Dr. Indrani Das of the Department of Botany. Over to you, Indrani.
Good afternoon. Thank you for being with us here. When education is concerned, knowledge is concerned, mankind and researches are concerned, when humanity is concerned, when our mother nature is concerned, the world is one. We are pleased to welcome Dr. Peter Reed, an eminent professor of University of Oxford, United Kingdom. He obtained his PhD degree in radio astronomy from University of Cambridge. Currently, he is a professor in atmospheric, oceanic, and planetary physics within the Department of Physics at the University of Oxford, where he has led a group researching the fluid dynamics of planetary atmospheres and oceans since the early 1990s. He is also a fellow and tutor in physics at Trinity College of University of Oxford. He has also held posts as head of atmospheric, oceanic, and planetary physics in Oxford from 2008 to 2013 and UK Met Office Joint Chair of the Oxford Met Office Academic Partnership from 2013 to 2019. He has been a member of space mission science teams on the Mars Observer, Mars Reconnaissance Orbiter, and Cassini missions with NASA. His works have been published in many international journals of reputations. He will be going to enlighten us about how climate and atmospheric circulation regime putting our beautiful planet into a planetary perspective. Dear participants, please join me in welcoming our honorable guest speaker, Dr. Peter Reed. Dr. Reed.
Thank you, Indrani, and thank you, Dr. Chowdhury, also for your very thoughtful comments. I will share my screen so we can begin the presentation. So I hope that is now going to work. Okay, I hope you can see my title slide. So as Indrani has mentioned, my theme this afternoon is concerned with trying to understand the circulation regimes of planets in general. The Earth is a planet that is very special to us in very many ways, but it's important for us to understand where it sits within the range of possible planetary configurations. The Earth is just one member of a family of planets in the solar system. It happens to be the only planet so far that we know of that hosts a biosphere, hosts life, but it is in many respects a fairly typical planet. And in the light of recent discoveries since the middle 1990s, we now know that planets surrounding stars are a very common occurrence. There are very many planets around within the galaxy and beyond. And this poses all sorts of intriguing questions as to what are these planets like? Are any of them remotely like Earth? And do any of them host life or have the capacity to host life? Well, these are background questions that motivate the kind of study that I'm going to talk about today. So I'm going to begin with Earth, and this is a rather nice movie that I hope comes through okay to everybody. So what we're looking at is a set of images of the Earth's atmosphere seen from geostationary satellites. These are satellites that orbit the Earth at a distance in such a way that they orbit the Earth in precisely one day. So that means that they will be able to view the same part of the Earth all of the time. And they're viewing in the infrared spectrum around about 11 microns, which is where the atmosphere is relatively opaque because of the variations in water vapor. And so what you're seeing here is water vapor visualizing motions in the atmosphere. Now we think of the atmosphere as being a sort of a complex turbulent fluid, but you can already see from the patterns that are evolving here before you that it is not a completely random circulation. There is structure here. You can see, for example, in the tropics, you can see the winds predominantly move objects such as clouds, mostly towards the west in the so-called trade winds, whereas at higher latitudes you can see wave-like structures being carried by very strong winds in the middle and upper troposphere. We're looking here at altitudes at around about 15 to 20,000 feet, or something like 6 to 8,000 meters above the surface. And it's this organization of the circulation that is what I want to focus on. So the organization of the Earth's climate and circulation, I guess, is probably familiar to many people. Has a number of distinctive features that we can see summarized in this this cartoon. So it has low latitudes in the tropics. The circulation is dominated by an overturning circulation in latitude and height, known as the Hadley circulation, after James Hadley, the 18th century explorer, and dominated by the trade winds, which are predominantly essentially towards the west. Whereas at middle latitudes, the atmospheric flow is dominated by strong jet streams that move essentially towards the east and are concentrated in the upper part of the troposphere at around about 10 kilometers or so above the ground. And these these jet streams meander up, back and forth, north and south, associated with what we call baroclinic cyclone, anticyclone weather systems. These are the sorts of weather systems that affect the latitudes of places such as in Northern Europe. The overturning circulation in these latitudes tends to be in what we call an indirect sense. It goes it circulates in the opposite sense to the Hadley circulations, and they're known as the feral cells. So this is, and then there's a kind of polar cell that is often observed in observations much closer to the poles themselves. And of course, this circulation varies on a seasonal time scale, mainly due to the tilt of the Earth's rotation axis with respect to its orbit. So we can ask the question, is the Earth unique in having such a circulation? If not, then how does it compare with what we see in the atmospheres of other planets? And we've been very fortunate to live in the last several decades with the advent of space exploration that actually has allowed us to visit most of the main planets in the solar system. And so we have a much better idea now than we used to have about what the other planets in the solar system look like. And it allows us then to ask the central question, which is how and why does the Earth's climate and its circulation differ from other planets? And if so, why? Why should these circulations differ? And in particular, what are the factors that are most important to determine the strength and the shape of a planet's atmospheric circulation? So this is a summary of the observed structure of the Earth's atmosphere. You can see the temperature as a function of latitude along the horizontal axis, and it's the height in the vertical axis. And so this is the structure of the atmosphere averaged along latitude circles. So you can see the temperature. So temperature tends to decrease with height, and it tends to decrease from equator towards the poles in a fairly familiar fashion until you get to the very high upper atmosphere, essentially into the stratosphere when the temperature starts to increase again. Associated with this distribution of temperature is the pattern of east-west jet streams. So the middle frame shows contours of the east-west wind velocity, which you can see the presence of these strong jet streams that feature centered between latitudes of of 20 and 60 degrees north and south. Associated with this pattern, then we see the meridional overturning circulation. So the bottom frame shows what's called a stream function. So you have to imagine the vertical and horizontal wind blowing parallel to the contours. So we see air essentially rising close to the equator, sinking at latitudes around about 40 degrees north and south, and then the ferrule cell gives is the middle cell in each hemisphere, and then a polar cell, as I indicated earlier, close to the poles. Now these are observed, but we can also simulate the atmosphere's behavior in exquisite detail, and I couldn't resist showing this movie, which is essentially a model simulation of essentially the same kind of fields that we were seeing in the movie that I showed in the very first slide. So this is an atmospheric numerical model with a resolution of about 10 kilometers across the whole globe. And what you can see here being visualized are clouds and moisture in the atmosphere, again being transported and advected by the winds in the middle of the troposphere. So we can capture an awful lot of the great detail that is manifest within the Earth's atmosphere. What about other planets? So other solar system planets tend to look pretty different from the Earth. This is a sort of collage of all of the main planets in the solar system, shown to scale. So the sizes of each planet are shown relative to each other, but obviously not in respect to distance from the sun. You can see the sun represented on the left, and then the next planet is Mercury, then have Venus, and you can see my cursor, Venus, the Earth is here, here's Mars, this is Jupiter, Saturn, Uranus, Neptune, and it even shows Pluto here at the very outermost edge of the solar system. And most of these planets, although not all of them, have significant atmospheres that we can study. So let's have a quick look at some of these atmospheres so you can get a flavor for the kind of things that we can observe. So we start with Mars. Mars is in some respects the most Earth-like of the solar system planets in terms of its atmosphere and meteorology. So what we can see here are on the left some images taken from lander spacecraft that have landed on the surface of Mars, and you can see sort of cirrus clouds being moved by the winds as viewed from the ground. The lower left image shows dust devil vortices. So these are convective vortices that lift dust from the surface of the planet and lift it up into these columns. And this is very similar to dust devil type structures that you can see in deserts on Earth, almost anywhere in Earth like deserts. And the right-hand frame, lower right, shows frost deposits. This was an image taken by the Viking lander spacecraft, so it's showing very familiar looking weather. But one thing that Mars does that the Earth doesn't do is that it can have extremely large-scale dust storms. So the top image shows a pair of images from the Hubble Space Telescope taken just a few months apart. The left-hand image showing relatively clear conditions, and you can see white clouds in the Martian atmosphere as well as the surface itself. And then sometime later, you can see that dust storms have erupted on the surface. They've carried dust across the whole planet in such a way that we can now scarcely see the surface at all. And these global dust storms seem to happen once every few Martian years. They happen at certain preferred times of the Martian seasonal cycle. So just to give a little bit of perspective again, so Mars is a somewhat smaller planet than the Earth. It's roughly half the size of the Earth. but it rotates at around about the same speed. It has a length of day that is just over 24 hours, and it has an atmosphere that is principally carbon dioxide with a little bit of nitrogen and other constituents, but with only something like 0.5% of the surface pressure. So it's a relatively thin atmosphere, but it's a thick enough atmosphere nonetheless to exhibit some quite interesting meteorology. Many features of which are quite similar to what we find on Earth. So Mars has polar ice caps, except that these consist of a combination of both water and carbon dioxide ice, because Mars is further away from the sun and its surface temperature is much cooler. It also has mid-latitude jet streams that you can see visualized here by a streak of dust that's being carried by this jet stream. And it also has wave-like anticyclone weather systems. And you can see a trough here representing one of those features. And you can also see that the winds are strong enough to actually lift dust to produce these extensive dust storms. We can simulate the circulation of the Martian atmosphere in some detail, and this is showing the same kind of fields that I showed for the Earth now, but this time for Mars, averaged over an entire year. And you can see very similar structures. You can see the temperature decreasing with height and decreasing towards the poles. You can see the presence of these large, strong upper atmosphere jet streams at middle latitudes, much like on Earth, except that the Mars's jet streams are somewhat closer to the pole. And you can see a meridional circulation that actually looks somewhat similar to the Earth, although it's in some respects it's a little simpler. You don't see such obvious evidence of the feral cells. You only see the Hadley-like circulations. But this is what Mars looks like in an annual average. If you look at an individual season, particularly at the solstice times, so for example during Northern Hemisphere winter, the pattern looks somewhat different. The temperature structure now is very asymmetric between the two hemispheres, with a very warm summer hemisphere and a very cold winter hemisphere. The jet stream in the summer hemisphere has almost disappeared, and the meridional overturning circulation is now dominated by a single large overturning circulation that crosses the equator. So very large changes in the circulation during the seasonal cycle on Mars. Venus is the other main terrestrial planet that has a very substantial atmosphere. The left image here shows an image of Venus in the ultraviolet obtained by the Japanese mission Akatsuki, and this shows very characteristic cloud patterns on Venus. Venus is almost entirely covered by clouds, but these are not clouds of water droplets. These are droplets typically of sulfuric acid, so not a very pleasant kind of environment. Venus is in many ways the Earth's twin. It's almost exactly the same size as the Earth. It's roughly 95% of the Earth's radius. But Venus rotates much more slowly on its axis compared to the Earth. So 243.7 days it takes for it to rotate on its axis. And it has a very, very dense atmosphere, 90 times more dense than that of the Earth. And that gives it this very intense greenhouse effect. So the surface temperature on Venus is very, very warm. Something like 750 Kelvin or so. Its circulation is also quite different to what we see on Earth. So we see a pronounced polar vortex, for example. Looking at the same fields for Venus as simulated in atmospheric models, we see that there are relatively small changes in temperature with latitude. The temperature only really decreases very strongly with height, and varies much less strongly in the latitudinal direction. But it also has very strong jet streams, but these jet streams that blow towards the east, effectively on Venus, extend all the way to the equator. So there are no trade winds on Venus in quite the same way as on the Earth. And the overturning circulation is now completely dominated by the Hadley type of circulation that extends almost all the way now from the equator to the poles. So we can kind of summarize that in this sort of comparative plot that was taken from this paper by Karatakin and his co-workers. So we see these meridional circulations are very different across these three planets. And so it's very interesting to ask the question, what are the main factors that actually distinguish these planets? If we look further out into the solar system, then we have other planets as well. These much larger, very different planets from the Earth and the terrestrial planets. So we have the so-called gas and ice giant planets. So we run from Jupiter on the left, Saturn in the middle, Uranus at the top right, and Neptune bottom right. So these are much larger planets than the Earth, and they seem to be made primarily of hydrogen and helium with other hydrocarbon materials that form their main constituents. And you can already see that they're also covered in clouds, mostly clouds of ammonia ice on Jupiter and Saturn, and on Uranus and Neptune, then the ice is probably a methane ice primarily that we can see being very prominent here in these images. The weather and climate on a planet like Jupiter is again very different to what we see on Earth. These are an animation of some cloud movements that we see on Jupiter. We can see that the winds are very much dominated by east-west jet streams, and with many jet streams that extend all the way from the equator to the pole.
I think and so that this is a nice. Yeah.
We seem to have an interference. Okay.
বড় সব সময় থাকে চালু তো কোথায় ছক্কা দিয়ে চাল কি করে চলে গেছে আরে চাল এটা কোথায় এটা এখানে নেই এটা এখানে কি আনলো এটা করতে গেল এখানে ছিল বোধহয় এখানে
Okay. So we see that the clouds are organized into these bands that run from that are very much aligned along lines of latitude, and so the circulation is very much dependent on latitude, and the difference in clouds may be associated with a whole sequence of upwelling and downwelling circulations that are associated with these very powerful jet streams, embedded within which we see these large vortices, such as the Great Red Spot, which is what we see here, which is a vortex that's been observed since the 17th century. So Jupiter is much larger than the Earth. It's 11 times the radius of Earth, but rotates very rapidly. It's a rotation period of nearly just under 10 hours. And so is under very different conditions from what we see on an Earth-like planet. Not only that, but we can also, only recently has a spacecraft been able to actually fly over the polar regions of Jupiter, and we find different circumstances all over again. These are some infrared images of Jupiter showing these intriguing regular patterns of cyclonic vortices. So you can see in the North Pole we have 8 vortices surrounding the pole, whereas in the south we have just these 5 with a single vortex right on the pole itself, which are still intriguing people as to why these features have formed. Oops. So to pose the interesting questions then, how can we begin to understand why these planetary circulations are sometimes similar or sometimes very different from Earth? And we can suppose that maybe the various planetary parameters play an important role. such as the size of the planet, its rotation rate, its distance from the sun, or its parent star in the case of an extrasolar planet, its obliquity, its angle of tilt with respect to its orbit, and various other features may be relevant. But maybe the composition of the atmosphere is also important. Maybe its density, its mass, its opacity to solar and infrared radiation, whether clouds form and moisture, does that play an important role? Perhaps even the presence of a biosphere may also be important. One might suggest, and of course the properties of the surface may also play an important role. There are many possible factors that one could imagine would have an influence. But the approach of a physicist is to try to be very selective about which factors to concentrate on. And the kind of question that we're interested in particularly is to find out which factors are the most important. And the way we can tackle this is to begin with actually looking at the properties of flows that are in models that actually make very, very simple assumptions. So we begin with the simplest possible model, but hopefully no simpler, in order to be able to study atmospheric circulation. So how do we model a climate system? The basic technique has been established for many years now for the Earth. So we solve the time-dependent equations of atmospheric dynamics, thermodynamics and continuity. So this is the conservation of momentum, energy and mass on a three-dimensional spherical grid that covers the entire surface of the planet and in altitude. We compute the various physical forcing terms that are actually driving the circulation. So this will be to do with the radiative transfer, the incoming sunlight, the outgoing thermal radiation. We may be able to represent clouds and moisture, the surface topography, the shape of the surface and its properties, and any boundary processes. And if there are any processes that we cannot explicitly resolve in the model because they're happening on too small a scale, then we have to find ways of representing these in a parameterized way. So this would include the effects of small-scale turbulence, clouds, convection, and chemistry, for example. Now, the problem there is that you have many, if you want to do this in a very comprehensive way, you have many parameters to define or to determine. And that's not really going to tell us very easily which parameters are then the most important. So what I'm going to talk about is some work that we've done recently in my group to explore the effects of varying parameters on a prototype atmosphere by using a very simple three-dimensional dynamical climate model. So we've used it's based on a dynamical model that was originally developed with the Earth in mind, either the PUMA model, which was developed by the University of Hamburg in Germany, or the ISCA model, which was developed recently by the University of Exeter in the UK. And these solve the basic equations for the conservation of momentum, energy, and mass with a certain resolution. We ignore any topography on the surface, so we don't have any, there's a flat surface, and we use very simple radiative forcing, either a relaxation to some prescribed temperature distribution with height and latitude, as we show here, or using very simple radiative transfer that is not specifically tied to any particular composition of the atmosphere, but just allows for incoming solar radiation and outgoing infrared radiation. And we have a simple representation of friction at the surface, and then we can vary either the size of the planet or particularly the rotation rate of the planet. And I'm going to talk about some work now in which we varied the rotation rate of an Earth-sized planet, and we're going to either slow it down to levels as low as 1/256th of the Earth's rotation rate, so a length of day of 256 Earth days, all the way up to 8 times the Earth's rotation rate. So in other words, a length of day that is only 4 4 hours. And we're going to ignore any effect of moisture or water or oceans on the planet. We're going to assume, we're just going to see what happens essentially if we were to ignore all of those features and just allow the dynamics to respond to the changing rotation rate. So just to convince you that this is not a totally crazy thing to contemplate. So on the left, what we show are the observed winds and temperature in the Earth's atmosphere. This is derived from the American Meteorological Institute. So the upper panel shows the temperature as a function of latitude and height, and the lower panel shows the zonal winds, so that you can see the mid-latitude jet streams. And the right-hand panels show what we produce if we run our very simple model under Earth-like conditions, so with the same rotation rate and the same the same distribution of heating and cooling, produces a patterns of temperature and wind that are actually quite similar to what we see on Earth. And so what we show now here is what happens if we now start varying the rotation speed. So the top left panel shows, well, all of these panels show the animations of the east-west wind in each simulation. And this is the east-west wind near the top of the troposphere, so at an altitude of about 10 kilometers or so. And what we're doing is varying the rotation rate. Here we're slowing the Earth down. So the top left is the equivalent of the Earth's rotation rate. The top right is at 1/2 of the Earth's rotation rate. Bottom left is 1/8 of the Earth's rotation rate, and bottom right is at 1/16. And so you can see trends already in what happens if you slow the Earth down. So you can see that the jet stream itself, which is the sort of red and orange part of the wind, starts to move towards the poles, and the wave number, the number of waves that you fit around a latitude circle starts to decrease. And as we get to very slow rotation rates, sort of 1/8 and 1/16, you can see that the main jet stream gets very close to the pole. But at the equatorial regions, you see that the color is changing and has actually now become an eastward wind rather than a westward wind. And that persists all the way down to these very, very slow rotation rates. Whereas if we go to more rapidly rotating planets than the Earth, so again, the Earth is top left, twice the Earth's rotation rate is shown top right, 4 times the Earth's rotation rate is bottom left, and 8 times the Earth's rotation rate is shown in the bottom right. And you can see now what's happening is that the mid-latitude jet stream that we see under Earth conditions now starts to split into more than one jet. And we see, first of all, 2 or 3 jets in each hemisphere when we double the Earth's rotation rate. And this becomes multiple jets in eastward and westward at the much higher rotation rates, ultimately becoming with many jets that appear between equator and pole in the 8 times Earth's rotation speed case. We can see these trends fairly clearly if we now look at the zonally averaged distribution of temperature and wind. So this is showing maps in latitude and height. So latitude along the horizontal axis, height along the vertical. The left hand shows the temperature structure. You can see how that varies as we slow the Earth down. And you can see that as we slow the Earth down, the jets on the right-hand panel move towards the pole, as we saw in those animations. And the overturning circulation, the Hadley circulation, also widens and extends towards the poles. Whereas if we increase the rotation speed, so this time the Earth is at the bottom, and the rotation speed increases as we go up, you can see that the zonal jets now move towards the equator and then start to break up into multiple parallel jets. And associated with each of these jets are separate overturning circulations. So the whole circulation becomes much more complicated and organized into these multiple zonal jet structures.
So the naturopathy, Ayurveda, adult care, pest control, and medical and wellness tourism is picking up. So if you are an entrepreneur, then you could look at.
Now we can understand this the organization of these structures by now looking at ways in which we can combine various planetary parameters into universal dimensionless parameters. This is a practice that people in fluid mechanics have done for centuries, in fact. And the way the way that seems most useful to construct these parameters is to look at ratios of various quantities, and in particular looking at ratios of some of the forces that act on the planetary circulation. And in particular, there's one parameter which measures the ratio of the inertial accelerations to the Coriolis accelerations, which are due to the rotation of the planet. And if you look at the different parameters that this corresponds to, it gives you a parameter that is proportional to the equator to pole temperature difference divided by the square of the rotation rate times the planetary radius, omega squared r squared. Another important parameter that turns out to be very, very important is a measure of the friction or the dissipation, the damping of motions in the atmosphere. So we can associate a time scale associated with the dissipation in the atmosphere. And if we look at the ratio of that time scale to the length of the day, then that gives us another dimensionless parameter that we can then see how that helps us in organizing and correlating how changes in the circulation vary. So if we just look at the values of these parameters, so the theta parameter, remember, is just go back, the theta parameter is this parameter, the delta theta over omega squared r squared, and the friction parameter is this thing. So that's what these parameters are, depending on whether we choose the mechanical friction or the radiative damping. So we see typically for these different planets, the theta parameter varies over many orders of magnitude. So for the Earth, it's around about 0.1. For Mars, a very similar value. For Venus, a slowly rotating planet, has very large values of this. So does Titan, the largest satellite of Saturn, which also has a substantial atmosphere. Whereas Jupiter actually has a value much smaller than that of the Earth, around about 10 to the minus 3. Whereas these damping parameters tend to be very large, apart possibly from Mars, where it's not quite so big. So if we now look at try and map these different circulation patterns with regard to these parameters, so we can produce a two-dimensional map showing the theta parameter on the vertical axis and this damping parameter omega times the frictional timescale squared along the horizontal axis. We can now see that these different styles of circulation now fall into a kind of clear order. And we see that near the top right of our diagram, we see these what we call super rotating atmospheres with jet streams that are very close to the pole, and the whole atmosphere tends to be moving towards the east. Whereas in the middle of the diagram, we see more Earth-like patterns, although this is the half Earth rotation rate case, which is a little bit more Mars-like, and Earth itself is around about the middle. And then as we move towards the bottom right, we get these multiple jet type of structures, which become more and more like the circulation that we see on the gas giant planets like Jupiter and Saturn. And we can see now, ordering the various experiments that we've done in our model. So this is showing theta, the delta theta over omega r squared parameter, scaling with the rotation speed, so from slow rotation all the way up to very fast rotation, and this is the damping parameter. And it turns out that if we compare these with the values of these parameters that we can infer for the solar system planets, they kind of order rather neatly. So the slow rotating plate simulations look much like what we see on Titan and Venus. The middle ones look like Mars and Earth, with the sort of single jet streams with baroclinic cyclones. Then the twice rotation rate looks quite similar to what we see on Uranus and Neptune, and the fastest rotation rate case looks very much like Saturn or Jupiter. And this dynamical similarity is suggested then if we characterize these planets with regard to these dimensionless variables. And it allows us to make predictions now, because if we take an Earth-like planet and reduce the rotation rate, say to 1/20th of the Earth's rotation rate, then we see a pattern that looks a bit like this. So this is the east-west wind as a function of latitude and height, with this strong eastward flow in the upper part of the atmosphere, this large-scale overturning circulation and relatively weak temperature variations with latitude. But now, if we look for a similar situation where the planet is now very different, but has the same value of this dimensionless parameter theta, so we can achieve that by taking an Earth, a planet now that has the same rotation rate as the Earth now, but is 1/20th of the radius of the Earth. So the product of omega r remains the same, but now instead of having a slowly rotating Earth, we now have a much smaller planet that's rotating at the same speed as Earth. And lo and behold, the atmospheric circulation looks almost exactly the same. So this is actually telling us that we can scale these planetary circulations, and provided we can keep these dimensionless ratio variables to be the same, then we can actually predict what different planets' circulation will look like. So we can play this game with regard to extrasolar planets. So there is a class of planet that we find around other stars that we don't find in the solar system, so-called super Earths. So these are rocky planets that are much bigger than the Earth, and we don't really understand very much about them as yet. But they have something like, I mean, they may have a radius that's up to twice that of the Earth. And if we take a super Earth, for example, that is rotating at the same rotation rate as the Earth, so the length of the day is the same as on Earth, that's actually, in terms of the product of r times omega, that's actually very similar to the twice Earth rotation rate case that we showed in our Earth-like simulations. So we can already predict from that what the temperature and the wind structure would look like on such a super Earth planet. So it would have a temperature variation that looks something like this, and it would have at least 2 eastward jets in each hemisphere, is what we would suggest. Have this somewhat more complicated circulation pattern than we see on Earth itself. Whereas if we were to take a super Earth and discover that it actually rotates much more slowly, perhaps 1/32nd of the Earth's rotation rate, then that's more like the 1/16th Earth-like case that we have already shown. And so that would have a pattern with only 1 jet stream in each hemisphere, quite close to the poles, with a Hadley circulation that extends all the way from the equator almost to the polar regions. So what are the implications of this dynamical similarity for our planetary circulation? It means that these model simulations and these model experiments suggest that the main structure and strength of the circulation just depends on a relatively small number of critical dimensionless parameters. And even very simple climate models can capture, therefore, a lot of the diversity that we actually observe amongst the solar system planets, simply by matching these principal parameters, as we've already seen. Now, the discovery of extrasolar planets, of course, gives us many more objects to consider. So the latest count I saw was there's around about just over 4,300 planets that have been confirmed by yesterday, according to this website, which catalogs all of these things. And so they must be exploring a huge range of our parameter space. But unfortunately, we have very few detailed observations. We can only detect the presence of these planets and perhaps locate them with respect to their parent star, and perhaps measure their size, and one or two other sort of gross parameters, but we can't we can't actually measure any of the details. But if we can use our dynamical similarity ideas, that means that we can infer quite a lot of information about their likely climate and circulation, provided we can estimate the values of some of these principal parameters. And that, of course, guides astronomers as to the kind of things that they should try to measure with these extrasolar planets. So in principle, it means that we don't really need to develop and run 4,000 different types of model for every single new planet. But we can build a kind of grand theory that helps us to understand the principles that govern the structure of all planetary atmospheres in this sense. But that's not to say that these simple models can explain everything. They can only tell us about the gross sort of properties of the organization of the planets. So we still need much more detailed observations, much more detailed models and observations, if we actually want to compare individual model predictions against ever improving observations. And we're going to see observations of extrasolar planets becoming much better in the near future, that will be able to tell us much more about these different planetary atmospheres, and will hopefully help us to improve our theoretical understanding of how all planets work. And if we understand in detail about all planets, then that is by implication also telling us and helping us to improve our understanding of the Earth itself. So I think that's a good point at which to stop. And I must thank you for your patience and your attention. And I'm very happy to take some questions if there are any questions. Right, I can see various questions appearing on the chat.
Okay, sir. Okay, sir. So, sir, should we enter into the interactive session, sir? Hello.
I'm sorry. Can you say again?
Okay, sir. So we are now in our interactive session, sir.
Okay.
So I welcome you, sir, here. Myself is Dr. Madhumita. So, sir, should I read out the question?
Yes, if you wish.
Okay, sir. So the first question is from Ronak Maitra. Okay. He asks, does the atmosphere of a planet depends upon the position of the planet in the Goldilocks zone? I repeat. Sir, I repeat, does the atmosphere of a planet depends upon the position of the planet in the Goldilocks zone?
Okay. If by the Goldilocks zone, I guess what you mean is the is the habitable zone, the so-called habitable zone of a stellar system. And so, well, various properties of the planet will be affected by where it lies with respect to the parent star. The Goldilocks zone is a range of distance from a given star that essentially helps to determine the average surface temperature. And the Goldilocks zone basically means that the temperature range lies within a range such that water can exist in a liquid state at some point within the planetary environment. However, there is nothing really there's nothing particularly special about the Goldilocks zone in that sense with regard to the atmospheric circulation, because that depends much more on the planetary rotation and one or two other parameters, but particularly in a sense how the atmosphere is heated and cooled, and that is affected probably more by the tilt of the planet's axis with respect to the orbit than where it lies within the orbit itself, with one proviso, that if you move too far out of the Goldilocks zone, particularly going away from the star, you may eventually get to the point where the equilibrium temperature of the planet is so low that the constituents of the atmosphere will then actually condense from a vapor phase into a liquid phase or a solid phase, and the atmosphere may then disappear. So in that point of view, the presence or absence of an atmosphere may depend on your location with respect to the parent star.
Okay, sir. Thank you, sir. So next question is from Nisha Tandon. That is, what is the theory behind the changing magnetic field of the Earth? I repeat, what is the theory behind the changing magnetic field of the Earth?
Well, this is not really an area that I would claim any particular expertise, but we know that the Earth's magnetic field is almost certainly generated by motions that are taking place in the Earth's liquid core. So the Earth's core is comprised mainly of liquid metals, mostly iron and nickel. And seismologists tell us that the structure of it is such that there's a solid inner core and a liquid outer core that occupies something like a quarter to a third or so of the inner part of the Earth, and as a result of motions that are generated inside the core, which is partly due to heating and cooling, but it's also, there may also be some mechanical and compositional stirrings that go on. This stirs up the metal, and because the metal is a very good conductor of electricity, then motions of liquid metal will also constitute electric currents, and that's essentially what generates the magnetic field. But because this is being generated by a turbulent motion in the core, then the behavior of the magnetic field that's generated may also behave in a chaotic fashion. Now there's various evidence that suggests that that there is still order within this chaotic behavior, such that there are cyclic variations. So the Earth's magnetic field grows and decays and reverses, much in a similar way to what we see on the sun. I know there's some interest at the moment because the Earth's magnetic field is undergoing some interesting changes. I mean, the magnetic field does vary in a constant way. There are various features that sort of actually move with respect to the solid Earth, and there are various features that seem to suggest that parts of the magnetic field are actually becoming weaker. So there's a lot of interest at the moment as to whether we are approaching the conditions that might lead to a reversal of the Earth's magnetic field. This will happen at some stage, we believe, but nobody knows when. and we don't have models that are good enough to be able to predict this. So this is something that is very interesting. We understand some of the principles behind what generates the magnetic field, but we don't know enough about it yet to be able to predict in any detail how it is going to behave in the future.
Okay, sir. Thank you, sir. The next one is from Samrat Bhattacharya. Is there any satellite in our solar system with nearly habitable atmosphere? Is there any satellite in our solar system with nearly habitable atmosphere?
Ah, yes, it's an interesting question. So the main moon of Titan, sorry, the main moon of Saturn, Titan, has a very substantial atmosphere. It's a largely nitrogen atmosphere with hydrocarbons. It's very cold, but it does have a substantial atmosphere that is rich in organics. So that has certainly prompted some speculation that it might support some sort of living organisms. Mars, of course, is the planet that everybody tends to turn to. But you mentioned satellites in particular, and I guess in terms of its atmosphere, Titan is probably the only one that comes to mind. But what is particularly interesting now is that people are discovering some of the icy satellites in the outer solar system have oceans of liquid water at depth below the icy surface, and it's the presence of these oceans that raises some interesting possibilities that if life were ever to be able to develop in these places, they could be sustained in principle in these oceans that are essentially buried underneath these very thick icy surface layers.
Thank you, sir. The next one is why this one is from Dr. H.K. Yadav. That is why tropical cyclones are not formed near the equator. Why tropical cyclones are not formed near the equator?
Ah, yes, that's an interesting question. It's a question of what the origin of tropical cyclones are. I mean, what processes actually set them off, and it seems to be well, it's a combination of several things. It's partly because you need some projection of the Earth's rotation onto the local vertical to be able to give disturbances some initial circulation, some initial vorticity. So they cannot form directly on the equator itself. They tend to form as a result of wave motions that take place slightly away from the equator, still within the tropics. And if you go maybe 5 or 10 degrees away from the equator, then there is enough projection then of the Earth's rotation that can actually allow the Earth's rotation to influence the development of these disturbances, and that sets them starting to rotate in the appropriate direction. And then once they start to rotate, there are then various feedbacks that are associated with the presence with the evaporation of moisture from the warm ocean. That then allows clouds to form and latent heat to be released in the atmosphere that then actually allows these things then to develop.
Yes. Thank you, sir. So maybe the last one, I suppose. This is from Abhishek Pariyal. What is the main significance of jet stream for climate change? I repeat, what is the main significance of jet stream for climate change?
Okay, that's a very interesting question, and there are many facets to it that I'm sure I don't have time to go into, and there are probably some things beyond my own understanding. This is a question that you would do well to put to one of my Oxford colleagues, Professor Tim Woolings, for example. This is one of his main research interests. But what we have been seeing with the onset of global warming during the late 20th century is that the jet stream has been moving systematically in latitude, and it's tied in with changes across the whole planet. We know that global warming effects tend to have their largest amplitude actually at very high latitudes. So we've been seeing very strong warming trends in the Arctic and in the Antarctic, particularly in the Arctic, with the melting of summer ice and so on. And that's associated with systematic variations in the equator to pole temperature contrast. And that will manifest itself by changes in the mid-latitude jet stream, particularly the subtropical jet stream. And it will tend to weaken it because you're actually reducing, by warming the polar regions more than you're warming the tropics, you're reducing the equator to pole temperature difference. And that will have the effect of actually slightly weakening the jet stream. And for those of us that live in these temperate latitudes, that can be important because it actually then makes it more likely that the jet stream will be able to meander more vigorously. And that actually can have important changes in mid-latitude weather, because it then allows us, for example, sometimes to experience tropical air more often, sometimes to experience polar air more frequently, and so it tends to enhance extremes of weather. Either we get extremely warm heat waves, as we've actually been enjoying such things just recently in the UK and in Northern Europe. But it can also mean that you may get very cold winters as well, because it means it brings some of the polar air further south than it used to be the case. So the jet stream plays it's at a kind of very important crossroads in the circulation, and so as the climate changes, it can actually have all sorts of very significant effects, not just in the region where the jet stream occurs, but also reflecting what's happening in other parts of the world.
Okay, sir. So can I read out the last one, sir, please?
Mm-hmm.
Okay, sir. This is from Samrat Bhattacharya. Do gaseous planets have only gaseous satellites and not terrestrial? Do gaseous planets have only gaseous satellites and not terrestrial?
No, that is actually not the case. So if you take, I mean, the largest gas giant planet is Jupiter. So the planet itself is composed principally of hydrogen and helium. But if you look at most of its satellites, the closest of the Galilean moons, which is Io, is actually a rocky body. It's actually highly volcanic in that sense. If you look a little bit further out, then most of the other satellites are, well, they're not gaseous, but they are predominantly made of ices. So they are sufficiently cold that most of the materials have actually frozen, and so they actually look like rocky objects, but the material is actually predominantly made of particularly water ice and other volatile materials, just with some rock kind of blended in.
So our interactive session is over, sir. Thank you, sir. Thank you very much, and it was a pleasure to have you with us. And actually, you took us to a ride to the meteorological world. Thank you very much, sir, and for clearing our doubts also.
That's
Thank
my
you
pleasure,
very much.
and thank you very much for the invitation.
Okay, sir. So we are really very sorry, due to time crunch. We could be able to read only few questions. If you have further queries, do mail us at naturetalksajc@gmail. So right now we have an announcement. So participant. Okay.
Madhumita, I'm.
Hello.
I have a small query to Professor Reed. You had been enlightened.
Okay, sir.
His address.
Okay, sir.
I had been having a news items on the very steady and fast depletion of ice sheets in Greenland. in an alarming rate. I know it's today the topic is about astrophysics. Even then, you are closer to Greenland. England is closer to Greenland, and we are also alarmed by this event. I had been having this sort of a news item on a few days. Can you throw some light and how could it be stopped? This steady erosion of ice sheets in Greenland. Thank you, sir, and thank you, Madhumita, for allowing me.
Okay. Well, I'm not sure I can answer this very authoritatively. We have indeed been hearing some worrying reports. I guess that the melting of the Greenland ice sheet has been accelerating in the last few years, and the problem seems to be that once you start the melting process, the meltwater manages to find its way down to the base of the ice sheet, and then acts as a lubricant. So it actually helps the ice to slide along the rocky material underneath. And what that tends to mean is that the glaciers, which tend to very slowly flow back down towards the ocean, of course, can now flow much more freely. So this is what we're seeing. Now you ask the question, can we stop it? Well, it's a very good question. The basic problem is tied, I think, very closely to this issue that I mentioned earlier, that because of the increase in greenhouse gases in the atmosphere, that is producing essentially global warming. The global warming effect is much stronger at high latitudes, and so that is, in a sense, what is accelerating the surface melting of the ice sheet. So, if you want to stop that in its tracks, then the only real answer is that you have to take greenhouse gases out of the atmosphere. And exactly how we do that, I think, is a very substantial challenge. And I don't know that anybody has come up with a viable solution as yet. So this is something that I think we need to throw very much at our younger generation. This is something that is needed urgently, I think, to find some way in which we can very much reduce our reliance on carbon for our industry. But not only that, we have already pumped large amounts of carbon dioxide into the atmosphere, and it doesn't go away very quickly. Some of the carbon is taken up by the oceans, but not enough. So the overall carbon burden in the atmosphere itself has gone up, and it's not going to go down very quickly unless you take active measures to remove it. And so that may be a major technological issue, even if you can solve the political or the geopolitical issue in persuading countries, and I guess particularly it's a particular issue for developing nations, emerging nations, particularly like India and China and Brazil and so on, who are investing substantially in building their industries. And the temptation, of course, is to use carbon in the same way as the rest of the world has done, and it's a very, very difficult situation to reduce everybody's reliance on carbon and to find alternative sources of energy. But anyway, I should probably stop there.
Thank you very much.
Okay, sir. So, sir, I need to ask a question. Alodi? Alo, ma'am, are you there? Alo, ma'am?
Yes, I'm there.
Okay. Ma'am, so you can give the vote of thanks.
Madhumita,
Okay.
there's a participant from Kenya. He wants to ask a question. Just allow him to do so. I mean, he's been waiting.
Okay, ma'am. Okay.
Hello.
Hello.
My name is Eric from Kenya.
Okay.
I'm sorry for asking question when the time is over.
No, sir, you can ask.
Thank you very much. I wanted to confirm from Dr. Reed about something concerning the dwarf planets and how many planets do you have? Is Pluto considered to be a planet or it's no longer a planet?
Ah, yes. Okay. Yes, that's an interesting question. It's been quite controversial, I guess, within the last 10 years or so. But Pluto is now considered to be what's called a dwarf planet, and it's therefore one of the most well-known members of this new class of planets. So the dwarf planets are these rather smaller objects, and they seem to be very common in the very outermost parts of the solar system. I don't know exactly how many we know about now, but there are certainly several tens of planets that are of these dwarf planet objects, objects that are of comparable size to Pluto, almost certainly icy objects, and these inhabit the region beyond the orbit of Pluto. And so although it may sound as though Pluto has been demoted in importance, but it's actually now being viewed very much as a prototype of a new type of planet that we're only just beginning to discover and to understand. So it's actually we can think of planets within the solar system to fall into one of three different categories. There are terrestrial rocky planets that occur in the middle, in the inner solar system. There's the gas giants that we find in the sort of further out, and then there's these dwarf planets, the so-called Kuiper belt objects, of which Pluto was the first to be discovered, essentially.
Okay, so sir, you got your answer?
Thank you.
Okay, sir. So, hello, ma'am.
Yes,
Ma'am?
I'm there. Yes.
Okay. Over to you. You just then you invite Sharmi. Okay, you give the vote
Okay.
of thanks. Okay.
Thank you, Madhumita. Am
Okay,
I audible?
ma'am. Yes, you are audible. Okay.
Thank you so much, Dr. Reed, for a brilliant, informative, and absorbing speech on climate, on today's topic, climate and atmospheric circulation regimes, putting Earth into a planetary perspective. I enlisted myself as a faculty member, but now I think I'm back to being a student because you have enriched us with valuable information and knowledge on today's topic. Your vivid description of the atmospheric dynamics of our planet and our neighboring planets has been a treat for curious minds. Your presentation widened our horizon of knowledge. Thank you, sir, for gracing our webinar. As to the theme of the webinar series, Connecting with Nature, it needs to be reiterated that nature is a storehouse of sustenance, the basis of life, the foundation of survival. We live and die in the lap of nature. Nature provides us raw materials, which man converts into resources by using his skill, his labor, his intellect, and his knowledge. With all its beauty, mysteries, and power, nature ignites our curiosity, allures us, and dares us. It arouses our sense of wonder, our sense of awe, beauty, and also our sense of goodness. We undertake voyages on Earth to space. We explore, we discover, we invent, we create history, we write literature, all with the purpose of achieving a better understanding of nature to bond with it. When we look around, we see colors, we hear myriad sounds, we see eternity, we see ourselves, all of which make us realize how precious life is, how important it is to share and care. Nature is thus a teacher, a healer, a pacifier, just like the lull after a storm, fertile soil after floods, rebuilding after destruction. Nature guides us towards immense possibilities. It is up to us to choose the best path so as not to destroy nature, but to nurture and sustain it, and in turn, nourish life on earth. Thank you all. Stay happy, stay safe. I now invite Professor Shormi Bhattacharya to present a slideshow of posters submitted by the students. Over to you, Shormi.
Thank you, Professor Alo Guho, and a big thank you to Dr. Reed for such an insightful session. Now, without further ado, I would like to start with a presentation of selected posters based on today's theme and issues. We have received posters from students across various disciplines and participating colleges. So let's begin. The first poster has been put together by Shayani Shaha, an MPhil scholar in School of Oceanographic Studies from Jadavpur University, Kolkata. The poster has been titled El Nino Event, Outturn of Atmosphere-Ocean Interactivity. She has beautifully presented the concept of El Nino, which is associated with rising temperature and heavy rainfall. She has charted the comparison of atmospheric and oceanic conditions during this phenomena, shown the effects of El Nino, its change over a century, its impact in Latin America and the Caribbean, along with its prediction. I leave the slide on for some time for everybody's visual satisfaction. Moving on to our next slide. It has been prepared by Shatadol Sengupta, a 5th semester student from the Department of Chemistry of St. Anandram Jaipuria College, Kolkata. The poster has been titled, When You Live in a Round World, There Is No Choosing Sides. Introduction to Global Climate Regime. There is a diagram of the Lorentz regime model alongside another diagram showing climate regimes around the world. Next, he has described history of the geological regimes. And lastly, he has described the issues and proposals over regimes. Our next poster, and quite a vibrant one, has been jointly made by Dipayan Sharma, Paritosh Bagh, and Saptarshi Dotto from the Department of Chemistry of St. Anandram Jaipuria College as well. The poster, titled Aurora Borealis, explains the concept of the northern lights and the effect it has on climate change. They have also cited how magnetosphere affects the aurora emission. I leave the slide on for some time. Proceeding to the next poster, it is from Shikha Singh, a 5th semester student from the Department of Geography of St. Anandram Jaipuria College. She has titled the poster, Climate and Atmospheric Circulation of Earth. She has portrayed the diagram of Earth's climate system alongside Earth's atmospheric circulation and has depicted climate change as well. The next poster has been prepared by Hani Biswas, a third semester student from the Department of Chemistry of Jaipuria College. The poster has been titled Signs of Thunderstorm. And describes the formation of thunderstorms. The chemistry behind this phenomena has also been explained. Our next poster is from Shweta Kesharwani, a fifth semester student from the Department of Geography of Jaipuria College. The poster has been titled Atmospheric Circulation and Climate Regimes. Now, this poster talks about the different models and classifications of atmospheric circulation on the one hand, on the left side, and its effect on climate and climatic classification on the right-hand side. We can also see the effects such phenomena has beneath. Our next poster, titled Smog-Free Tower, the Giant Air Purifier, has been put together by Sarthak Basak, a fourth semester student from the Department of Zoology of Jaipuria College as well. He has beautifully arranged the different aspects of a smog-free tower, starting from its meaning, structure, working principle, example, importance, especially in India, limitation, and ending with a conclusion regarding the smog-free project. The final poster consists of 2 slides and has been jointly prepared by Abhilasha Ganguly and Gairika Bhattacharya from the Department of Zoology of State Anandram Jaipuria College, titled Mangrove Forest as Eco-Health Regulator of Sundarban Delta. They have shown how the mangrove forest helps in the sustainability of the soil, biodiversity, environment, and livelihood of the region. In the following slide, they have portrayed the ecological fragility and vulnerability of the Sundarban mangroves and the delta as a whole. With this, I end this presentation. Thank you. Now, I would like to call upon Professor Srimonti Chaudhary for announcing the 3 best posters. Over to you, Srimonti ma'am. Srimonti ma'am.
Thank you, Shurmi.
Thank you, ma'am.
The 3 best posters. Yes. Hello. Can you hear me?
Yes, yes.
Yes, ma'am.
Yes, Professor
Yes,
Chaudhary, we
ma'am.
can hear you. Please go ahead.
Okay, fine. Thank you, Shurmi, for entrusting me with the task of announcing the 3 best posters from today's poster presentation. Each poster in this competitive section was unique and impactful in its own way. However, as judged by the designated panelists, the 3 winning posters are as follows. Third position, Smoke-Free Tower, the Giant Air Purifier by Sharthak Bose, 4th Sem UG student, Department of Zoology, Shet Anandram Jaipuria College, Kolkata. Second position, When You Live in a Round World, Introduction to Global Climate Regime by Shotodol Sengupta, Department of Chemistry, Shet Anandram Jaipuria College, Kolkata. First position goes to El Nino Event, Outturn of Atmosphere Ocean Interactivity by Shayoni Shaha, MPhil Scholar, School of Oceanographic Studies, Jadavpur University. We congratulate all the participants, hope to see more of and wish them all the very best, all our participants. Now, to offer the vote of thanks, I invite Oindrila Ghosh, faculty in the Department of Computer Science. Over to you, Oindrila.
Thank you, Dr. Chaudhary. I would like to take this opportunity and thank Professor Reed for his illuminating talk. I would also like to thank Honorable Principal Sir and Dr. Ashish Ghosh, Administrator of SA Jaipuria College, for their encouragement and support. Heartfelt thanks to the members of the IQAC for their cooperation extended, and I sincerely acknowledge the love and interest shown by the entire SAJC family. Thank you, audience members, for your active participation. With this, I would like to end this webinar with a promise of being back with our second chapter on 4th September 2020, themed on cyclones and its tracking and monitoring issues. Goodbye to you all, and wish you all a very nice day. Thank you.